That's a problem. What's in Pico? Okay, so I'll describe. In Pico, the pseudocode directory containing some crucial and some pseudocode you need to program. Some actual and some pseudocode you need to program. During the bootstrap, that's the main function. Your OS needs to. So remember the bootstrap. All these are potential midterm questions. Okay. Header files. How does it do the name mangling prevention? Like I said, OS bootstrap. The purpose of bootstrap. Initialize all the kernel data in the kernel that kernel needs. Initialize the control environment the kernel needs. Create a first process. In our case, it's called idle proc, and then load the first process to run, and the main will ends. Doesn't come back, and then the first process runs, takes over the computer, and whenever there are events like timer interrupt, is guaranteed 100 times a second. It will wake up kernel. Kernel, hey, you run. Timer interrupt you. Hey, kernel, you run. Timer interrupt you. 100 times a second in our platform power up. It can be programmed to 10,000 times a second faster, but we leave it a default 100 times a second. That means your kernel has only 1/100th of a second to complete the service. The remaining of the 1/100th of a second is left for the process to run. Okay, you don't want to leave it too small of a few instructions to run time. You want to have the kernel small. The kernel service routine. So this is time. I want to draw it like a time device. So the CPU runtime in a timeline. Timer interrupt is going to occur to interrupt at a frequency of 100 times a second. Okay. So there you know, context switching will happen, timer service code will happen. Okay. It will switch into timer service. So that's the kernel service that needs to be carried out. How long does it take? So that's the question. You want to have this minimized as small as possible. And in order to continue to switch it to run process, that's how it started. When the process is running here, process I runs. Then we switch back to process I until the next timer interrupt. Okay. And then switch it back to process I again. Okay. We can switch to a process J if we choose to. In the end of timer service, there will be decision making, schedule to decide, and then the process loader to load what's being selected by scheduler. Another process, J. Okay. So you see the timer gets this time sharing runtime timeline. And then you understand the services on the kernel must be really small. Okay. In terms of phase one, there's only timer interrupt services. In the future, there will be more services events interrupt. Okay. So all kinds of service events may not be synchronized like timer that can occur any given time to interrupt the running process. The kernel has to service it and then come back to resume that process or select a new process to run. So all the service codes must be efficient, small. Yeah? All right, so that makes it hard to say timer is programmed at a much higher frequency. And then the period to run CPU instruction is less. In order to run CPU instruction with less instructions, distributed among kernel instructions, kernel services, and processes will be even harder to guarantee this frequency can be carried out. Okay, make sense? You can program this to 10 kHz. Then you can see original, this period is separated by 1,000 times, 100 times smaller. So that becomes very few instructions. And we have a Pentium 2 400 MHz, very old target PC. Still the throughput, as you know, close to 400 meg in CPU instructions. Even a single core, single pipeline, okay, per second. Yeah, so 1/100th of a second can execute 4 meg instructions. Yeah, that's a lot, you know. I think your whole OS project to the end of the semester is probably compiled less than 4 meg instructions. so you say, oh, why are we using this old stuff? It's faster than you can handle. Okay, it's still much faster than you can handle. All right, so that's the thing. 1/100th of a second. The CPU execute 4 million instructions, peak throughput, I guess. So it's good enough for us to test with a small target PC running at a very small clock rate. Okay, so that so I apologize. I cannot say let's go to like 747, jumbo jet or Dreamliner 787. We got to start from a single propeller engine from World War I. You got to first push the propeller. Boom, 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 boom. That's a timer, okay? You just fire 100 times a second. And you say why? If you walk into the 747 cockpit, just to explain those panels, the instruments in the panel will probably take a whole semester. Because they are all interlinked, we cannot say, let's just try one. Okay, so that's is your first OS writing. Okay, the idle process, the purpose of that, idle process will be defined in the pseudocode. You can see runs the infinite loop, showing its PID 0 once a second. Kind of like time on lab, we have a loop to show something once a second. And then the timer event also kicks in the background and triggers the kernel timer service that will also execute 100 times a second to assert itself to do something else. It could be every 3/4 of a second that it displays a dot, like the demo shows you. And number 3, the timer service counts the runtime of the process in order to monitor if it reaches a time limit. So we can use it to control, kernel can use it to control the time limit of a current running process. Okay, so the timer service can do a counting and then count into a number that reaches the time limit, a constant, then the kernel can choose to preempt this process and select a different process to run. Okay, and the pool of runnable processes are queued in the ready pick queue. Okay, and when they are created, so they will be selected one after another in a round robin fashion from the pool of ready to run PID queue. Number 4, the kernel, when detecting a special key being pressed on the target PC, it will service it like an event. And we're going to have 2 keys pulled in the kernel code. One is the N key, one is B key. You can pull key in the timer lab by console KB hit. If it's true, then console get job, you can get a key from the sample in sample.c. And then if it's N key, the kernel code can call this subroutine new proc service to create a new process. And the new process has its PID queue here in the ready to run PID queue. Okay. So if you push N key 3 times, there will be 3 new processes queued in here to be taken out to run. one after another, okay, run up to the time limit, and then be queued back to this queue. So they will take the round robin runtime. When they run, they display their own PID. So you will see a PID 1, 2, 3 also gets to be displayed. And BQ can give you a chance to go to the GDB prompt. This will execute breakpoints in the kernel code. When you program it to execute breakpoint, and that gives you the kernel, gives you the GDB prompt, so that you can quit. At the GDB prompt, you can quit. You can do GDB debugging, print something of a variable, for instance. Does that make sense? Or I should skip reading because you're not, is it, I really don't care. I just want to get this done, like abracadabra, it's done. How are you going to get that abracadabra done? That's the question. Okay. So I'm going to invent a device on my smartphone app. As my smartphone app, it will take a picture of HTML and then understand what it wants and then make program. Yeah. And that app is you. That's why company hire you to do that. Okay. Okay, number 5, one thing the timer service performs is to upcount the runtime of the process. And so we got to count something in order to know is it count up to a certain thing. For every process, there's a count that's required. And we put it in the process control block for that process. So when it counts out to this time limit, you can actually see the constant name, time limit. The process is suspended with its PID moved back to the tail of the ready queue. So basically NQ back. And then the timer service also dismiss IRQ0, just like what you did in the timer lab. The question will be like, if you don't dismiss IRQ0, what's gonna happen? Okay. Number 6, the process scheduler on the kernel code dequeues the first PID from the ready PID queue. That's a runnable process. So scheduler is called upon to do that. So you will think, shall I switch process? If it does, it will look at the ready hit queue. All the ready to run PIDs are there to take out the first one in the front because it's round robin, and then use that for the loader to load and run the first process. I mean the new process. Otherwise, it will select the original one that was interrupted by timer and resume that. Number 7, all the available PIDs are initially queued in the available PID queue. So this is not use the PIDs from 0 through 19. We're only going to test 20 available PID queue. 0 through 19 is queued in there. The initial state is available for all of them in the PCB. So PCB, for every process there's a PCB. Initially they are not used. So what's the state? The state is that not used, available, not created. It's just a shell. So that's the resources to be dispatched, to be created. And then the state will change it to ready from the available. As a new process created, PID from the available PID queue is taken, DQ'd out. Each PID is also an array index in both arrays. The process control block is an array because we're going to have 20 PIDs indexed into this array. And the PIDs are also indexes. Indexes are also PID. And then the process runtime stack is another array. This is a 2-dimensional array. For every process, there's a 4K number of bytes runtime stack. Okay. To create a new process, the new process service code initializes the PCB and creates a process track frame. This is the CPU context called the process track frame, created in the runtime stack to be loaded by the process loader. The process loader loads that track frame into the CPU, becomes the CPU context, and that also includes the instruction pointer, points to the new function to run. Okay, so that's the mimic of running a new process. The PID is then queued to the ready pick queue. The state of the process created is changed to ready. Okay. Number 8, the val pick queue initially primed with numbers 0 through 19. All the PIDs are available at the beginning. While the ready pick queue is initially empty, the first process to be created is the idle prod process by the new prod service during the OS bootstrap. The PID of the idle prod is 0 because it's the first one created to take out from all the PIDs available in the available pick queue, but that will be 0. And as an exception, process 0 is not queued to the ready pick queue. Do not queue that in the ready pick queue. It's always available to be selected by this guy. If this has no other process to select, it will select 0. This is how it's coded in the P code. Okay, and its runtime, our idle prod does not need to be upcounted in the timer service. The timer service do not need to count the runtime of the idle prod. All right. Number 9, each of the 2 PID queues has 20 integer array in the queue array at the size, which indicates the number of PIDs currently queued in the array. This will be more explained in people. The code file tools.c means to code like IQ, DQ functions to facilitate the IQ and DQ functions, plus a my B0 function to clear all the bytes to 0 from a given character pointer, char star. So we can clean up the DRAM. We can use that function to clean any region of DRAM we want to clean. The kernel needs to do that. A process control block contains 4 different things in phase 0. State, this is the process state. We have available, ready, and run, 3 different states to start. And then we have 2 integers called runtime and total time. They are counts from 0 and counting up. And they are driven by the timer interrupts. We have the timer service code to count it. Okay. For one process, the current running process will be counted, outcounted. And it will be compared against the timer, the time limit. And here's the total time. Total time is accumulated from the runtime for that process after creation. Okay. For the length of the process until it's terminated, the total time is counting the timer interrupts. And then the try frame type pointer. There's a pointer pointing to a try frame type. And try frame type is a structure. And there's a pointer in the PCB. This is the address location, byte location of the CPU context whenever the process is interrupted. So we save the CPU context into a try frame inside the runtime stack. The pointer to that place is here in the PCB. The actual place for the try frame is in the runtime stack. Okay. So this can be reloaded back to the CPU. The process loader can load it back the traffic to resume the runtime for that process. All right, so the try frame, the content of the try frame is to be created when a new process is created by the new prod service. So the code there will initialize the first CPU context in terms of the try frame in the runtime stack. When the process is first created, we allocate a PID on the available PID queue and use that to index into the PCB array to use that PCB. And index into the process stack, the second array, to use that as a process runtime stack. And in that process runtime stack, the try frame will be created, initialized. And they, in phase 1, contain only these 4 things, which is 8 different integers to accommodate CPU, 8 different registers as a push stack space. And then the EIP instruction pointer, the code segment selector register, CS, and extended the flag EFL. Okay, so these 4 things are needed to constitute the initial track frame for a very simple process. Does that make sense? So remember, time of lab event occurs, it will push by hardware, and then we can push A, and then we call the C lane timer handler. When timer handler finishes, we come back to part A in the assembly code, and then IRA will part EIP, CSCFL, all from where the stack pointer currently points to in the stack, in the memory. Okay, so there's a CPU register, our stack pointer, that's in the background, it's being used for any push and pop commands. And the instruction pointer is like a program counter, it increments itself automatically. So these are very basic CPU architecture concept. Okay, so whenever you hear push and pop, then you say push where, pop where the stack pointer points to. You gotta think, where does the stack pointer points to right now? Okay. The whole magic at phase 1 is to understand the 2 pointers in the CPU, which are the instruction pointer and the stack pointer. The instruction reads instruction from low memory, main function, execute it. Maybe it has a loop, you will do something like this, loop back, and then go into another subroutine and loop inside, and come back, and then to the outer loop that calls subroutine, maybe a different subroutine that does a loop and come back. So the instruction pointer is pointing to the fixed compiling instruction. The stack pointer, however, is coming from the top, from the high memory, push down, pop up, push down, pop up, pop up. All the subroutine has the local variables also are used inside the stack to allocate the local variable address. And then where the subroutine ends, come back to the main routine, it abandon all these space, come back to the original point the main stopped calling the subroutine. Okay, from there. So the main will resume the old stack. And then it switches from main function bootstrap to a process. Okay, to a process. The process also has instructions. In our process, very simple one, it does a loop. And then it will do those few things that needs the stack. And the interrupt occurs, it will switch it to here, to the kernel code. Switch it to kernel code, hardware will help push the EFL CSEIP. And then to the kernel code, push A, will push the A10 register, and then switch to kernel stack. I should say still putting here. And then switch to kernel stack, and then we're going to resume the kernel from here. Okay. This happens 100 times a second. Okay. So if you have a GE drama class, you're going to have like a drama stage presentation on timer lab. If your brother play a process and one guy plays the kernel, that's gonna be very busy. So then you're gonna have to switch this in slow motion and get faster and faster. And with a background clock that ticks faster. Okay, so you understand now, they are the 2 registers you had to know switching from where to where, and back to where. Number 12, the idle process is created during the OS bootstrap code in the main function, and the instruction pointer on the CPU EIP of the process traffic points to the code of the idle prompt. So when we create a process, we create a traffic in the runtime stack to be loaded. And inside the traffic, it contains the EIP, points to the functions to start to run. So when the process starts to run, the process runs this function. For other process created while pressing the N key, we're going to set the EIP, the track frame, to point to this one. Okay. So there's only one idle prompt. Other NT will create the same user prompt, but they will display their own PID. Okay, so they will be different. There is the same code, but it will be showing that it can differentiate itself with a different PID because that's a different process, even though they run the same code. Okay. Number 13, the timer interrupt event must be dismissed. That's how it was done in the timer lab as exercise. And otherwise, the PIC will not notify the CPU for the next timer interrupt event, thinking the CPU is still busy with the old timer interrupt. Okay. All right, deliverable. By now, you should have formed your OS team with others. Maximum 3 people, okay, maximum 3 persons per team. And so you'll be like one guy coding, the other guy sit aside watching the code. The third guy go to get pizza and code. And your favorite drink? Perfect. And then you take turn hopefully. Yeah. And mail the instructor the OS team name and member names, similar to naming a variable in programming code. A team name may not use spaces or special symbols, and it's case sensitive, and it's socially sensitive, okay? And how many times the people will do Tiger Kitten, because I mentioned Tiger Kitten. Number 2, submit only the source code files. Do not submit any other files generated by the compiler or speedy tools. So all the source code file I need to compile and verify things myself only. Okay, do not submit output files or any intermediate.o files or make file that I will generate it myself. The make file. Okay, only these .c, .h, and .s. Even you copy by .h, you still submit it. Okay. Penalty will apply if fail to follow the above instructions, including any accidental clobbering or incorrect placement of files in the Dropbox folders of the server host Voyager. Okay. So to do some typing, shell commands, the good old-fashioned shell commands. Yeah, is it okay? Your fingers are not hurt, right? You have all the 10 fingers, right? All right. So. Or you can have a good project, signal project that there's a mobile phone app. You can do coding not by typing but by dancing. Dancing. This is F. This is L's. every keyboard you have a dance move. Yeah. So I enjoy programming. I also enjoy dancing. Combine the two. Tango will be a little hard. You need another person. Yeah. Augmented reality. But it's really hard to balance without a real weight. So maybe you can carry a bag of rice or throw it around. So the TDB will be a different dance, right? Okay, so I'm just trying to say, learn some shell commands and editor commands that will give you at least you don't use it anymore in the world. You're gonna be a CEO, CFO, talking about money but nothing else. But that's okay. At least you understand there's such a thing called programming tools, debugging tools, and why you need that, and why do you prefer to use BI than Notepad? Okay, and then here you won't have problem in creating clever up the folders. Okay. With a drag and drop, that doesn't work. Okay. All right, review questions is for you to think about. If you can answer these questions, you probably understand this project better. Okay, this space better. So those are for you to prepare for midterm exam.
Question. Do you want all of the team members to submit the same assignment, or just one?
Just one in your own team folder. Just like the timer lab, you create your login folder. Team name is just a unique folder.
Can you do a one-person team?
Well, yeah, you can do one-person team, solo team if you choose.
This is phase one, yeah.
But got to make sure that it is one person team. Some people say, I'm a solo team, you just give me more credit. But your code is the same as all other three. They are all solo. I just made the whole class one team. Well, we don't just have the whole class as one copy of exam. Yeah.
That's a good idea.
And I will give you all the grade that I share among all the class members. I'll give you A. Just one A, you got to share. Your diploma will be like having 30 names on it.
Oh, wonderful.
Your paycheck will be like, your card is 200. So still you have to everybody find a job to share that, to be a good socialist. Socialist. Don't blame me. I voted for Bernie Sanders. I'm a total socialist.
Socialist.
But I don't social that way. I don't social at all. That's why I study computer. I don't want to talk to people, okay? And many of us at that time, because we really don't want to deal with people, that's why we study computers. These days, you don't have Facebook? No, I don't. What are you? Are you a monster? You don't have Facebook? I have a flip phone. I don't have a smartphone. I'm not smart enough. Or I'm too smart. I'm smart enough. I don't need a smartphone. But who's laughing now these days? The original computer study people like us, we use the computers in the office to work. We never use it for socializing or for entertainment. These days that is synonymous to entertainment. Computer becomes consumer electronics. We study computer because we believe the computer will save the world. And very naive, young people. But now we think that at least he can entertain the world. And I don't have internet at home.
Wait,
People say, huh? What do you do for entertainment? What has it to do with entertainment? For millions of years, we don't have internet. You play basketball. You dance. You can do dancing, yeah. Mm-hmm. You can do whatever you want that's better for your body instead of, sitting there, swiping the phone. I'm not saying it's bad. People say, all the scientific studies say the computer game is good for your brains. So is basketball. And also for your muscle.
You gain the hand muscles though.
Our thumbs getting shorter. So you see, but who's laughing now, right? All the hacking security problems. I don't have it. I don't exist in the internet.
Here it goes.
Do you have a TV?
I do. Okay. I don't have cable. I made my own antenna.
Oh.
And HD antenna is very easy to catch, and it's high resolution. It's all real news, local news. The tree fell in nice street. You can verify it. Well, big news too. The house burned down.
You see the smoke. Just look out.
Something really happened. So internet right now, you see the effect of all the fake news, starting from the Japan earthquake. And that's the time I realized that's the end of internet. And the Google bought YouTube, and then they started to keep asking everybody, do you want to monetize this? Do you want to monetize that? And they want to look at the Japan earthquake search. Then some guy sitting in Scotland, sitting there. Yeah, about the Japanese earthquake. It's bad, isn't it? One quick question, So you watch it, then you realize, that's not about the earthquake. It's just this guy sitting in his living room, getting money from you building. the idea that's at the end, that's the bubble. Everybody's living in our own bubble. That's totally different from when I was student like you sitting there, we believe internet should be free. It's not meant for banking use, DoD or whatnot. They should build their own net. Internet is for the people. It's just like fresh air, that's the meaning of the original, World Wide Web internet. We used to have T-shirt that I'm part of the World Wide Web. Are you part of the World Wide Web? You just create a web page called Hello World. You get a T-shirt. But yeah, so that's the belief at the beginning of internet and people learning computers. Yeah. But it's all changing now, so I don't know if it's changing for the good or bad though. To me, it's kind of mostly for the bad. Richie and Townsend. I'm not spelling this. So two guys invented the Unix. Look at the pseudocode. Pseudocode here. Entry.s. I just go from the top to bottom. Just first scan through, first parse. So here, the kernel stack is defined here. It's not defined in kernel.c. For other C type of definition of a global kernel data structure, they are defined there. Except this one, the kernel stack is actually defined here in this file. So be clear here. And then this is going to load the process. To load the process, load the trap frame, we say. The trap frame is the data structure in the runtime stack of that process. And we're going to call the process loader with the address of the trap frame. The syntax will be something like this in the C code. And then it's being passed over. This is an address. Trap frame is a term that everyone uses in the OS world. You say trap frame, people understand what you mean. It's a process trap frame. Why is it called a trap frame? Because when we suspend the process will have an image mapped into this data structure. And this is the CPU context and other type of things loaded back to the CPU to run into the living form. And then when the process frozen is to extract those vital information from the system into this traffic. Okay. So every process has this thing when it's not running. Every process does not have this thing because this is loading to the current computer to run. Okay. So it's the frozen state of a process. Okay, that's what the traffic is. It's trapped inside this data structure. And this is a C function call. Okay, C code. There's a subroutine call. And we're talking about the assembly code here. Assembly code here is going to have the compiler compile into the runtime stack. This address will be pushed in. So this is the process I run pin. And then so the stack has a traffic, and the PCB on the run pin is a data structure that has a traffic pointer. Okay. This traffic pointer is a byte address points to here. This is a process runtime stack. And this is the content called traffic. So it will be given to the function like this. The address is pushed in the runtime stack of the kernel. Kernel runtime stack is AK runtime stack that we saw the declaration. So this address is copied into here in the kernel runtime stack. So that is the traffic pointer. Is pointing to here. Into this location, like that. So that is the calling on the subroutine. Because why? Because you know it's going to call sub. To call sub, the parameter needs to be pushed. Compiler will compile the C call function call like this. The subroutine is the process loading. And the argument to push in is that in parentheses. Okay. So this is instruction. This is kernel instruction. Okay, that represents this. And the stack pointer is right here at that time of push. So stack pointer will move down and right above the content of this argument, which is that address. Okay? So to continue run from the assembly code's view, the critical argument passed over is above the ESP 4 bytes. In the 32-bit domain, each push is 4 bytes of an address, 32-bit address. Okay? So the stack pointer is now here, so you can see the stack pointer above 4 bytes. In the Intel syntax is like this, as you know. The base is stack pointer. 4 is the offset. Right? So that is where we extract the argument passed here. So we're going to move the 4 bytes above ESP to EBX, and then we're going to use it to override ESP. So basically, it's to switch stack pointer from kernel stack back to the process runtime stack. Okay, so this is where the stack pointer is going to switch from here to here. Once we have this content, which is this thing here, move to DP, okay. EBX, EBX. So the content from here move to EBX, and then override ESP. The actual code uses the E for 32-bit register. Okay, override ESP. So the ESP switches from here, kernel stack, into the actual place that has the traffic. Traffic data structure is here. And then we can start to pop. Okay. Start the popping, pop A, pop all registers, and IREN. There are two statements. One is pop A, one is IREN. Just like the end of the timer lab. The timer, in the timer lab, you saw the call of the CNAME timer service and come back. Okay, let's take a break. When timer entry executes, this stack pointer in the CPU still points to the process stack. After popping the traffic, the stack pointer starts to use below. And whenever event occurs to build a traffic, it will start to build from where the stack pointer is, somewhere inside the stack. And then this stack pointer is what is important now, yeah? Because this is where the traffic is, okay, after we push. So the position of the stack pointer, we copy to ECX. And then we need to somehow relay this information to the kernel code. Then the same way how this got its parameters is used here. We clear the direction flag in EFL like preparing call the C program. And we have some switchings of the DSCS data segment selectors into the kernel space. And using the hexadecimal 10 in the EAX to prime the DSCS. And then here is what happened. We're going to load the effective address, 32-bit L. Kernel stack plus this copy to the stack pointer. So what does that mean? We declare kernel stack AK. So this will move to the end of kernel stack. Okay, we declare AK kernel stack. We want the stack pointer to start from here to push down when kernel starts to run. So we have this address called kernel stack plus AK. So this is the position calculated. Together, the sum override the stack pointer. So stack pointer move from there back to here, back to kernel stack. You see that's everything here is kind of like the reverse. So here we push A. After the hardware has already pushed the EFL, CSEIP, as the event occurs. This happens in the background by the hardware. And then push A is going to further push 8 different registers. We have the space for it. And this whole thing becomes traveling again. Okay. The whole thing becomes traveling again. And this is where the stack pointer is right now. So this information we need to pass to kernel. Kernel will save it in the PCB to complete the whole process, coming back to kernel. So we're going to switch the stack pointer to kernel space. Top of kernel stack from byte 0 to 8191. Altogether 8192 bytes. So here, this is called the kernel stack, byte 0. So wherever this is actually is in the whole DRAM, is labeled here. So this plus this one, 8192, is gonna be right over. Okay. So if you pass 8192, right over here. And this is where we're going to override the stack pointer too. So the stack pointer is going to be set here. Set here. And the Intel processor works like this, the stack pointer. When it pushes, it moves down by 4, -4. And then override the 4 bytes, including this byte. Okay. So that is 10898. So then -4 over here, this byte is 8188. 81, 89, 81, 90, 81, 91. So these 4 bytes will be the data. And then the stack pointer rests at 81, 88. Okay? So whenever next push occurs, it -4 again. And then here is the first byte of the 4 bytes. 81, 84 to 81, 87. That's why we add 8192 to override the stack pointer to set it here. Okay, so stack pointer is gonna be initially set here. And then we can push the ECX, which is this guy. Okay. The stack pointer copy to ECX, the original one. So ECX is this address here. And then we override ESP with this new number. kernel stack plus 8192. So stack pointer switches from pointing to there to pointing to here. Then we push ECX. Okay. ECX will be pushed inside here. So the content here is ECX. That is the address of the original traffic. Okay. We only have one stack pointer in the CPU. That's why we juggle like this. Okay. So we push the ECX there. We clear the directory flag. We clear. I clear twice. And then we only need to clear here. And then call the kernel C code. Okay, call kernel C code. So the kernel code starts to run. Kernel code starts to run similar to this. It will pull the ECX from the argument. So this ECX will be put in the argument. When you have a C function written with argument, it's kind of compiled to obtain that argument from the top of the ESP, 4 bytes. The location of this argument. Okay. The locale of this argument is 4 bytes above stack pointer. Okay? That is the kernel stack now. So the stack pointer starts to use this, the full stack on the kernel stack. Okay, and the top has a value ECX, which is a copy of ESP before ESP switched to kernel stack. And it was the traffic pushed at the beginning of here. Hardware pushes the EFL CSC IP first, then the software starts from here. Does that make sense? Okay, so this is the hardest part of phase 1. Okay, hardest part of phase 1 is the stack changes, the traffic construction. Okay, so whenever time interrupt occurs, there will be a traffic build in the process runtime stack. We want the CPU stack pointer to switch from using the process runtime stack to the kernel runtime stack. But this information needs to be known for the kernel function to receive it in order to save it into the PCB. Okay. Then this can update the PCB traffic pointer. The PCB for each process has its state, runtime, total time, and traffic pointer. This is the most important one in the PCB because this is how we can run. The kernel can load the process by knowing where to load, where this traffic has been built. So here, the first thing you do is to save this argument to PCB of the running process. Okay. And then our kernel code can use it to call this. Okay, to start the process again, resume the process again, or can switch to a different one. So remember, at the end of the kernel code here, whatever it needs to do, service time interrupt, pull the key N key, B key, service time interrupt. Okay, we'll talk about kernel.c to show this in more detail. At the end here, it will do the process scheduler and process loading. And the process scheduler can choose a different one, which is okay, meaning that this one will suspend until next time the process scheduler gets to choose it. It will be eventually chosen again because it's round robin. Okay, does that make sense? And then this is the runtime below what we call them. This is the statement. So whoever is selected as a new run bit not the old one, but the new one, from the available PID queue, the PCB should have this information. Okay, for whatever selected. Because when every process comes in, when kernel code runs like this, the kernel will save the argument passed over to the PCB for that process, the current running process. Okay. So when processes are not running, they have this information in their respective PCB. That points to their respective runtime stack that has the traffic suspended. Okay. Frozen. Okay. Process frozen here in the traffic. To be animated again, traffic is loaded back to the prime loader call. Okay. So that's the all right. So that's the entry.s. So let's connect with other things. Kernel.c. All right. The kernel.c. You put your team name here, member name here, and this is includes. Okay. Then we have the kernel data structures defined here. We have running process ID. That's what the scheduler selects. And the queues, the PID queues, we have ready PID queues, available PID queues, 2 of them. Initially, all the PIDs are in the available PID queues. When you push N keys, it will be gradually taken out to create ready PID queues. Okay. There's a PCB array. This is a process runtime array, runtime stack. This one 2-dimensional. The first dimension is index, which is the PID. The second one is a 4K byte. And here's a unique kernel data subroutine. This will initialize all the kernel data, set them to 0 or to -1. We want to designate -1 to run pip to initialize it, meaning that there's no running process selected yet. And we're going to clear 2 PID queues. Use the my B0 to clear 2 PID queues. My B0 is one of the 2 functions you write in the tools.c. And enqueue all the PID numbers into the available PID queue. Okay. So you put 0 to 19 into the available PID queue by calling enqueue function from the tools.c in a loop. Okay. And then init kernel control. This is similar to what we have on the timer lab. We're going to check out where IDT is, locate IDT, and we show the location on target PC. And then we call the fill gate to fill out the entry timer, just like how you did in the timer lab. We call the fill gate subroutine function PD gave us this extra E. Fill out the entry and the timer constant 32 with a timer entry, that's the address to put into that entry. And then program the mask of the PIC, programmable controller, interrupt controller. And here, the scheduler logic is here. The process scheduler wants to set running process ID. If it's greater than 0, if it's 1 or greater, return. There's no need to set. When run pip is not greater than 0, meaning if it's 0, -1, initially it's -1, we need to set. We set by picking out from the ready pick queue. If it's empty, then we have to set it to 0. 0 is idle part, we run idle part. Otherwise, we dequeue the first one in the ready PID queue to be the run queue, to set run queue to that PID. Accumulate the total time by adding runtime to it. Okay. Accumulate total time by adding runtime to it for the selected for the selected run pin. Okay. Whenever we select the run pin, we're going to also start to accumulate the total time from the last batch of runtime. Then reset runtime to 0. So the newly selected running process will start with 0. It will start with 0. So whenever a process selected to run, it will run up to time limit because we started from 0. And then the timer service will upcount and compare to the time limit. Okay, that happens in the timer service. All right, let's see the bootstrap. Bootstrap is main. The main initializes kernel data by calling that subroutine up there and the control, and then calling the uproc service to create the idle proc. Okay. So you want to put idle proc, basically the function name is as the argument. So that uproc service can use it to create the first process. It will take out the avail PIDQ, the first one in it, which is 0, number 0. And then proc schedule is called, which we saw is going to set the run pit from -1 to something greater than 0, or at least 0 for idle proc to run, if there's no other process to run. And then proc loader will be given the address of the traffic on selected run pit, similar to this syntax. So the PCB of the selected running process ID indexed in the PCB is a data structure. It has a traffic pointer, given it as the argument on the process loader. So the process loader can set the stack pointer on the CPU to it, where the traffic is recorded in the PCB, pointed to here. And then this can be popped, the traffic can be popped into the CPU. And that includes the instruction pointer pointing to the function to run that function. Okay. So the new proc service in the service.c will explain how this is coded to create that traffic. Okay, how to create that traffic. All right, so when we're back to kernel, now here's a bootstrap. Main is bootstrap. Main will load a process and ends. There's no return. Main has no return. Okay, it loads the first process and it will end. Return 0 is really never executed, but just for the purpose of the syntax of main, compiler once. But this statement is never executed. Once we call this proc loader, CPU will switch the instruction execution to that process. Okay, never come back. The kernel comes back because the timer interrupts. We come back to kernel, given the argument that is a traffic address of the running process. So we save it. Okay. We save it back to the PCB of the running process. Update it. Update it. This is not the original address. Okay, to be rest assured. This is during the runtime of the running process. The runtime of the running process can be anywhere. The stack pointer can be anywhere. It's using the stack for different purposes. The instruction is not the first instruction anymore, so stack is not clean. And then the kernel called the timer service, because the reason that the kernel happens is the timer interrupt. So it will call the timer service, which will upcount the runtime and check it against the time limit, okay, and other things. And the key, we can pull the key here, the console KB here, can be called upon to see if it's true or false. If it's true, and we're going to get char, console get char, to see if the key pushed is N key or B key. If it's N key, we call this new proc service, just like we did in the bootstrap. But this time, we're going to create user proc. Instead of idle proc, we create a user proc. Okay. And then if it's B key, call breakpoint. So we can go to GDB prompt to quit or do debugging from there. So you can always push the B key to test if this thing is going, this kernel is going. If it's not going, probably the timer is not happening, the timer interrupt. call process scheduler and then load the process. The last two statement is similar to this too. The bootstrap. The bootstrap also has the last two statements, okay, similar to here. At the end of the kernel is going to end by calling scheduler and loader to load a new process or the old process when this is saved, the current running process. Process schedule may change around it. The time of service may preempt the running process if it runs out to time limit. Does that make sense? All right. So that's the kernel. The kernel is very small right now. It will get bigger. The constant here, we're going to have this loop here, so we can have a count of 1.6 million to call the delay of 0.6 microseconds using this to constitute 1 second delay whenever we need. There's a time limit set at 200. So 200 timer interrupts 2 seconds. That can be checked against the runtime count. And then the process number 20, the queue size is 20, process stack size is 4K bytes. The constant timer entry is 32 here. For the IDT, entry 32. Okay, so types. There are types that the kernel data structure has. We list them out here. A function pointer is what you had in the timer lab as well. For the function name is a pointer to a function. And the state type is going to have 3 states available, ready, run. A process has 3 states right now. And the type def, the C type def is to define the type. Okay. Type def define the type. 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 Okay. And here is an enumerate number, enumerable numbers, 0, 1, 2. Okay, so basically it's a constant 0, 1, 2. The definition. This means it's a constant 0, constant 1, constant 2. Okay. In the same as if you define 3 constants instead of using the syntax. But any one of these things, okay, is a constant in composition of a type. So if we say a process PCB has a state type, meaning that the value we can accept for that state here is this, or this, or this, or 0, 1, 2. Okay. They represent like an unsigned integer, 0, 1, 2. And the traffic type we saw already, we have 8 registers for push A, pop A, and the hardware will push EFL, CSC IP. The IRET software instruction in interrupt return will pop in reverse of the push. Then it will start from EIP, pop EIP, pop CS, pop EFL. The PCB type has a state, has the 2 integer counters, counting the runtime and accumulate to the total time, total the number of time interrupts since the creation of the process. And here's a traffic pointer that points to a traffic type. The traffic type is this. And here, the queue type, the PID queue type has 20 integers to queue maximum. And so you have 20 slots of seats. And the size is the valid numbers in that 20 seats. Okay. So don't get confused by this. Okay. So this is a 20 seat space. PID are put in there. The PID happen to be 0, 1, 2. Looks like seat number. Well, you can imagine that could be 100, 200, 300 different PID numbers. Okay. So the valid numbers in the queue is the size. If the queue is empty, the size is 0. So the content of this array is gibberish. Don't believe it. Okay. If the size is 3, then the queue has 3 good numbers, PID numbers only. Okay. And how to NQ DQ, that will be explained in the tool style C. The process, style C, okay, the process, style C. There are two processes. One is idle prop, one is user prop. Right now they are similar, okay, similar. You can see idle prop, forever loop displays 0 because its only possibility is PID is 0. Okay, the only possibility for its PID is 0. Loop number of times, 1.6 million of times to delay for 0.6 microsecond delay. So this altogether can approximate about 1 second delay. Okay, this in B, in reading a byte from this I/O register, numbered at 128, or has a decimal in 80, that will cause the CPU to delay 0.6 microsecond. Okay. Okay. So the only purpose of this I/O device is to delay CPU. Okay? It has no other use. And then the user process here also has a forever loop to show the its own PID. Its own PID right now is a round pin. Okay, so we just display round pin from the user process directly here. So instead of CRUD, we can change this using the get PID service call in the future. And then we loop 1.6 billion times to delay for 0.6 microsecond each. And that will approximate 1 second delay. Without a delay, this thing is going to be shown too fast for us to reason. Okay, these two. So we have a break here in order for the human to look at the display in the 1 second interval. Yeah, so you push N key is to create this. Okay, Bootstrap creates this automatically. Okay, and this will run at the beginning. So you will see it displays 0, 0, 0 if you run a demo. But every 3/4 of a second, a dot also shows up because that's from the timer. Okay, just like the timer lab. Something in the background displays that dot. That means the timer is working. If you don't see the dot, the timer is not working. Okay. And user prop, if you push N key, one of this will be created. If you push N key twice, 2 others will be created. And the PID of them will also be shown, respectively, when they run. Okay. How long will they run? 2 seconds. Okay? 2 seconds. So it displays PID and then wait for 1 second. Displays its PID, wait for 1 second. Okay. And then timer count. The runtime count will be 200. If there are other processes, if you have 1 and 2, they will alter among them. Okay, between them, 1, 1, 2, 2, 1, 1, 2, 2. Okay, like that. If you have 3, that will be 1, 1, 2, 2, 3, 3, 1, 1, 2, 2, 3, 3, like that. And if you don't have any, it's starting with 0. Okay. If you have N key pushed, the scheduler will prefer the ready pick queue. Okay, ready pick queue has 1, 2, 3 in it. It will select those. But don't believe that it's always 1, 2, 3 in that order. Okay. Right now it appears to be because there's no other interrupts. Other interrupts can say terminate process 2. Then all of a sudden process 2 is gone. You have 1, 3, 1, 3. 2 becomes a tail of the available PID queue. So after 19, then 2 comes up. Okay, maybe 18, 17, 18, 19, then the 2. If you create all the processes by pushing N keys so many times. So the order of the PID shown in terms of being selected to run in the round robin is not regular. It will start to scramble when we have more and more processes and services going. Some processes can cause sleep for 2 seconds. Some processes can cause sleep for 5 seconds. And then the process wake up early, they will show up early. The process will wait if they sleep longer. So when they come out, they will come out in all different order. Okay. Does that make sense?
So when you run your own code, you want to test it slowly and think about what's gonna happen and verify that, verify with that. Okay, so process.h is just prototype those two process functions, nothing there. And surface.c, okay, so here's the big one. So you have only two surfaces right now. Timer surface is underneath. Let's look at timer surface first. Timer surface is when we like doing the timer lab, we can count the tick. Okay. So here we want to count is the runtime in the PCB of the running process. We count it and then check against the time limit, the constant 200. If it reaches that equal, then we will set the state to ready and enqueue the running process ID to the ready pick queue, and then reset the running process ID to -1. And then at the end of the kernel, process scheduler will reschedule with this being reset. Okay. You say, what about here? What about here? Here is kind of like every 3/4 of a second you want to display a dot from here. So we do need to have a static counter inside this function, like the timer lab. We can count from 0, and every 75 we can display a dot on there. You can use the same logic like the timer lab. You reset it to 0 and display a dot. Or you can mod the internal count. Whenever it becomes 75, you display a dot. Okay, here we say we don't want to outcount the runtime for the idle prop. So if the running PID is idle prop 0, we don't need to do the rest. Okay, it's simply return. Okay. Exact. Okay. So if you count it, it means the time limit. We cannot preempt it. Okay. If we preempt it to the tail of the ready queue, then there's no process to run. Yeah? Or you can say the process scheduler will pull it out again. So it's futile to be put in there. So the run pin is 0, we don't need to count the runtime for it. When idle prop is selected to run, also means there's no other processes, 1, 2, 3, to run. Yeah? So there's no competition. There's no need to preempt it. Okay, idle prop. All right, let's look at the process creation, the service on top. So you put your N key from the kernel.c. Kernel.c pull the key, N key here, call this one here, new prop service, like an event. We don't have fork right now. This should be done by a fork call, okay, the fork service call. But now we just use N key. And we call this, given the function name, user prop. And or is idle prop. If it's called from the main bootstrap, is given with the call here, idle prop. If it's N key, is called here with the user prop. And here, the size of the available pick queue is 0, meaning that we run out of PID. So we just display a message called no more process. Okay. So basically, there's something wrong with the internal kernel condition. This type of condition is called kernel panic. Kernel panic means that there's something wrong with the kernel runtime. And we return, we cannot create. Or you can, alternative is to execute breakpoint. So you go to TDP to debug. Get a PID from the available queue if we pass this point. We didn't return, we didn't execute breakpoint. We can DQ a fail pick queue because the size is not 0. That means greater than 0. Okay. It shouldn't be the size shouldn't be -1. If your size is -1, there's something wrong with the kernel code. Okay. The kernel code logic is wrong. So here, get a PID and then the B0, the PCB, and the process runtime step. Okay, to clear them. And then you say why? Well, it would be nice if you clear them. If you don't clear them, it has residues of previous processes that use them for that. So the state is set to ready, and then the queue it to the ready pick queue. Except idle prop. Idle prop, we don't want to queue it. Okay. So Bootstrap calls this with idle prop. Then the first available PID DQ from the available pick queue is gonna be 0. So we're not going to queue it to the ready pick queue. And then the try frame is going to point it to its step to create a process try frame. The try frame has 3 values we care about: EFL, EIP, and CS. The EFL is going to be filled in with constants. This is the default EFL deflash register default value, or the interrupt enable. This is a bitwise, or that's the adding the flag bit of this one. Okay, this one is a unary pattern. So to be added to the default deflash value to enable the interrupt. So we don't use STI. Okay, time of lapse we use STI to enable. Here we build the try frame to load to the EFL directly with the flag enable. Make sense? Okay. Okay, fill out EIP to process pointer. Okay, so that's passed here. Function pointer will be where the EIP gets. And then the CSC will use this building function, the speedy give us get the current CS from the CPU, that function. So basically it's the assembly code copy the CS to the to return, and then put it into the CS field of the traffic. So okay. So this thing in here, that thing here is in the speedy2 user include. Okay. So if you want to find out what they really are, do we have time to do that? It's something that I leave you to explore if you want to know the detail of the flags. Let's grab from here. This directory passes is slow. You can see the command. Grab the EF interrupt. It's in the sub directory. So the EF you can see here, this is macro bit 0, bit 1, bit 2. Which bit is 1? Okay. So that's the macro of bit 0, meaning that the rightmost, okay, 1 bit is set to 1. Okay. So basically 1 bit is set to 1. So interrupt is bit number 9. That will be set on to allow CPU interrupts. If we OR this in, OR the in. Okay. Default value is just 1. Keep these bits on. Define PIC for bit defined in the speedy flames. Define a bit. Where's my cursor? So I see where my cursor is.
It's on define like that midway.
That's the
Okay,
yeah.
So on this byte, I'm gonna find define bit. Bit field. I don't see the micro for bit. For the bit field. It's very convoluted. So this is IO delay. This is where we in B hex 80. Bit micro, bit field, name width. Flames and limits. Bit field, name width. Define a bit field, name width. It's probably not here. I think it's gonna be somewhere below. Macro, bit macro, in the bits. Yes, BD says bits. Right here. Bits of something is the left shift of 1 to which position? Bit 3 will be a 1 shift 3. Oh, that makes sense. That's 1 0 0 0. Bit 0 is this one. This is bit 3. Others are 0. Bit 0 is the original one here. Bit 1 is here. The position is 0, 1, 2, 3. Okay, bit 2 is this one. So that's the single flag definition of which one position is the flag, which flag. Does that make sense? You say, this is really low level. Why are we caring about zeros and one? Where do we have zero? Where do we have one? Yeah, but it can make you bitcoins. It's $20,000 if you can get the bits right. If you are more hardware inclined, then you understand each bit is actually a switch. It's an on and off. Yeah. Like, well, I don't care that bit. Okay, let's turn the whole circuit power off. Boom. No internet, oh my gosh, I'm in hell. No bits unflipped. The spirit of engineer is DIY. So that's why people from the past, computer engineering students, people say, oh, you are just like Marines. You are sent to them to find. You have to improvise everything you have. So that will test your tenacity of curiosity. You should poke into the VD2 user and look at it. And then you will see other files. You start to explore. Oh my gosh, there's abundant of knowledge is there. Then you will never look at Microsoft OS the same way as before. you will pay them respect. Just kidding. Okay, so that's the services. The .h is very simple, just prototype the services. But sometimes you need to have this include. When compiler complains something, it's because many times you're missing the include to define certain things like this. This is keyword already built in C, but compiler do not understand this user defined, and that is because it's here. Okay, so you got to understand you include something for what purpose. You got to understand it's not. I'll just include everything, like Java, people learn Java, import, what do I need to import? Just import everything. So when you compile hello world, it's like 2 gigabytes. Which electronic is going to accommodate that? Just in case, that's how the virtual machine came along. People who cannot install software correctly, just get a whole virtual machine in. And then you're going to have a virtual network. Just get the whole virtual network in. Get the virtual world in your computer. Everything will work. But that footprint, is it possible to sustain? The virtual machine drains my laptop power right away. All right. So, but then again, the teaching, the moral of the story is that if you are billionaires, you have no problems. You just put down enough money, they will be accomplished by somebody. Everything has a price. Yeah. But after saying this, smart people like you understand that's not true. There are certain things money can never buy them back once they are lost. Environment, fresh air, fresh water. Doesn't matter if you're a billionaire trading air, it's not gonna come back again. We lost it. The air, the water, the ocean right now, as you can see. So they say, there's a saying that best things in life are free. Actually, are those things currently free? You can never buy them, you can never sell them, and you can, once you lost them, then that's it. All right. So what do you think? Let's insert your feedback. Will this be on the test? Okay. There's nothing wrong. That's a proper feedback because you are very pragmatic in that sense. Will that be on the test? Yes. 2 star C, okay. So this is the last one of the programming thing. Include these, and you also have to think that why do I need to include that? Because there are certain things here. Which one needs to type this? Which one needs to type that? Okay. Which one needs to have the speedy thing? And I didn't really point them out. Clear my B0. Okay. Clear DRAM my B0. There's a C program building function library runtime function called B0. So we're going to have our own, for every function, we're going to have our own. We cannot use the C current runtime library. Otherwise, it's kind of like swarm intelligence. For every question, you just ask the, what's that thing called? Alexa?
Alexa.
So Google thing. You just call your friends and they have an answer. But we got to do everything ourselves. Okay, you cannot follow things like, oh, I'm going to use that print function. We've been using that console print function. We're going to try not to use it in the future. We are our own from the video memory hex P8000. We know that's a memory address, video memory address. We should be using that as a console display. To write out simple device drivers for display. And here you have B0, we cannot use that. You use that, the runtime will fall back to the Linux PC. Okay. This is where you program your MyOS.di to download to the target PC to run. So everything should be self-contained here. Okay. All these things are not. These things are runs over here. Okay. The console one is this, but not these two. And all the goodies, English and whatnot, they're actually running here, and the result is changed over here. So when you have program code do that, it's not real. Okay. And then you might as well run everything here. What do you need to have this? Right? But the key is that we want to make an OS totally run here without any communication. So B0 is a building C function. We're going to have our own, giving a pointer to a byte location and the number of bytes. We want to clear the number of bytes from that location towards the high memory, not towards the low memory. So the concept of high-low memory comes along. Okay? That's why you have a direction flag bit in the CPU. Direction flag bit in the CPU. So you have a memory, DRAM. There are two ways that the Pentium processor can operate things. One is the source, one is the destination. The source has a size. The size reads backward. The copy is to copy this portion into here. Okay. And this is the low memory, this is the high memory. Yeah. So it's kind of strange if you have the other way around. You have the source and size copy to destination, or the size should be forward towards the high memory. This is the size from the source. Destination should copy like this. The copy should do it like this, yeah? And sometimes they overlap if you don't specify them correctly as you do programming algorithm. So that will be a big problem if you copy in the wrong order. And then you say this copy to here. Okay, let me expand this. So this is the source. This copy to here, and then this copy to here, and then this copy to here. Finally, at the end, you're going to have the source already written, copy to here, copy to here. But these two are wrong. These two actually the original first two copy here. Okay? So the overlapping copy, very dangerous, as you know. The order must be right. In this case, you got to start from here, and then you back up here, and then finally come down here, override here. Then it will be okay. And of course, that's the algorithm design and also the recognition of the memory mapping. depending processors, like many processors, has complex memory movement capacities. So that's why we need to have CLD. CLD, clear direction flag. Okay. And that's for the C function name. So we call the C function da da da. And then all the C function, you have P equal Q. Okay. That is a copy. Okay. You have I equal J. That's a copy. Yeah. And then you have I in here. You have J space in here. Then you say, okay, how does it copy? You know, I copy to J. Yeah. So this is the sources. This is the size. Okay. It's not that the source size is backward, and the copy is not copy backward, copy forward. So the clear direction, everything go forward from low to high address, the logic. Okay. Otherwise, you have all the variations from high to low, and that is not what I is. I is from low to high. The first byte is low address, total high byte, total high address. All right. When you do I equals 0, it's B0. Okay, 4 bytes. If I is 4-byte integer, they fill with 0. Yeah? It's just that we inherited from the mathematical notation, we have this type of syntax. Okay. You say this is copy? Yes, this is copy. We have copy. Main copy. Okay. In C is a built-in main CPY. Okay. Main CPY destination, source, size. Okay. And here you have B0. Okay, B0. The destination and size. The starting point is the size is 4 bytes. Okay. And you say main copy, the destination is I, the address of I, the source is the address of J, and the size is integer, if they are integer type. Some people wrote the size is J. But strictly saying, the syntax for size of in C code is a type. What that type is not about the variable name. Okay. And the destination, to start 0, the first byte is I. Follow 4 bytes toward the high memory. Okay, that's I equals 0. Does that make sense? All right, you got to get rid of sometimes the original traditional way of programming, because those are inherited from the mathematical practices. Okay. And if you have a definition of I in Java, then I should have an add method built in. Okay. So you need to add into J using I, accumulate J with I. Okay. It could be this method, or you can have a 3-argument method, I with 100, or I with another variable K, add to J. Okay. So you can see the method should be built into the object if everything is treated like an object. Okay, then you have the I max. You know what the max value can be, and I minimum value is for the 32-bit. Sign the 2's complement. The minimum should be negative 2 gig. The maximum is positive 2 gig minus 1. All right. So this is also why you need to recommend people start learning computer programming, avoid using object-oriented tool. That just confuse them. You wanted to learn using Chipmunk basic programming that really start to understand the procedural nature of the programming statements. If they want to go into how computer really works, then they got to think about using C memory copy B0, this type of thing to explain the assignment. Okay, then they really recognize every identifier is a DRAM region. Okay. So here, loop the size of bytes and set them to 0. So basically, it's just one line code in, like, if you look at B0, how it's coded. Okay. And you code it the same way, then you know that it's the destination and source and the size. And you can think about it's a char pointer is a assigned integer or unsigned integer for size. Then definitely this is gonna be the source destination. Wait a minute, destination source. So the destination, this is not copy.
It's just tricky.
Destination, what it points to equals to 0. No? And then it's a loop. Okay. So the loop, how many times? The size number of times. Plus plus. BST plus plus. Starting from DST, where it points to given 0 and then incremented for the size number of times. It's a loop. And this one, the syntax is strictly not 0. 0 is an integer. This one points to 2 is a character. So basically, you want to chart it. Okay. So what it points to is a character pointer. So the content should convert into a character to give it to where it points to. Okay, where it points to is a character. So that's the idea like that. And in C, you can write a one-line code for that. Okay. But you don't need to be so concise. Okay, so condensed. And then the DQ NQ explain how the queue works. The queue we wanted to work is an integer array to queue numbers. And this integer array is 20 slots. So the index is 0, 1, 2, 3, all the way to 19. Okay. And we have a size to indicate the size currently of the data, number of data in the queue. Starting with 0, we can use the size as the index as well to know that is where we need to enqueue something to. Okay. So we can do the enqueue with the pointer that points to a PID queue type. Okay. And we're going to have an element to enqueue. The element to enqueue is a PID or integer. Okay. So basically, this PID needs to be put into here. And then we increment the size becomes 1. Okay, so the size can tell us the queue is not empty. Also can tell us array sub 1 is the next place to enqueue. All right. So we're going to do this again. And then we're going to have another PID. Okay, and then the size becomes 2. And that 2 gives us the index of the next available place to enqueue. Okay. Then the condition, of course, precondition to check is that the size is not too big. Okay. And then we have the constant to check if the size equal queue size, that's too big. to NQ. So basically, you can display error message, the queue is full, cannot do it, return, so abandon this. Or you can go to GDB to debug who's calling this without checking the size. It's better that you program your code, check the size first of the queue before you use NQ. Okay. You say why? Because the exception handling at the upper level is easier to decide what to do. Instead of blindly calling here, and then this one doesn't know where to go. You cannot call the rescue subroutine from inside the NQ function. Okay. That's from outside to determine by looking at the size first before NQ is called. In order to deal with the exception from outside. Not to call NQ, but to do other things. Okay, so what about DQ? DQ will be the opposite. Let's say we do 3, and then the size is 3. So sub 3 is available. We have NQ, this 3 times. I'm saying these 3 PID may be any numbers. Okay, it's not, they're 1, 2, 3. They are ABC, okay, 3 different numbers. Depends on what is being NQ at that time. So this is the state of the queue. And then for DQ, we're going to check, okay. DQ, we should check instead of size is too big, check if the Q is 0, size is 0. Then bang, we can DQ, yeah? But the treatment here we prefer to do is return -1. Okay, return -1. Question?
So if the size is, so basically if the array is full, would the correct practice be to increase the size of the array, or would it be to have the operating system do something with those processes?
We got to abandon the NQ. We display error message. It says size is full. But we should have the upper level before calling NQ to deal with it. Yeah. So the upper level can check queue size to see if there's an alternative. Okay. So that upper level can decide if there's an alternative, do the alternative, or show the error message there. Okay. Or going to breakpoint. There are 3 different possibilities to do. But once the subroutine, like a 2 subroutine is called, then it has no choice but just to stop right there. Upper level will have a better context to decide. Go in to call this or not beforehand. Check the queue size. DQ also, if we're already inside the DQ, the code inside here, that is, okay. The code inside here is that we have no choice, we have to stop. And here we can return -1. We have a chance to have a feedback by the return. DQ is a integer return function because we want to take out one PID to return. That PID is an integer. NQ has no, it's a void return function. If it's a void return function, so it's void return function, there's no feedback. Okay, so you cannot, from the upper level, I call it, maybe it will return something, and then I'll deal with it, yeah? But there's no status return. This one has. Okay, so that's called a POSIX compliant. In the operating system writing, people say that's the POSIX compliant. They want to, the people support this is a policy. All the calls should have status return, always. And the return status is not DQ result. Okay. Any result should be put into the argument by giving a pointer to be filled in by that function. Okay, so this call poses compliant. The call the portable operating system, something I forgot. Okay. So that's the early days. We know people have the enthusiasm to study operating system. So every function, the return is the status code. Okay, whatever function call that is. And whenever there is a need for something to be filled in, given from the address here, there will be address of that data structure. In this case, it will be returning, okay, filled in the address given, that's a return PID to DQ. So the address of that local variable being given. So the DQ function filled in there, okay. And then the status is returned, like 0, success, 1, error, what kind, etc. Okay. So this is the standard verbose error table that the system can accommodate. So every system call should be this format. That's what they propose. But inherently, we didn't have all things like that. So we have gradually, started to do something like that. And return is 3, meaning that you successfully sleep for 3 seconds. If it also returns a